Welcome to The Explainer. Today, we're tackling a topic that, let's be honest, most students dread: electrostatics. Yeah, it's often seen as the most confusing, most intimidating chapter in all of physics. But what if I told you that its entire reputation is built on a big misunderstanding? What if the hardest problems in this chapter actually have the simplest solutions, just hiding in plain sight?
Look, we're not making this up. Every physics teacher hears it every single year. But here's the thing, we can't just skip it. It's not just another topic you can gloss over. It is a massive cornerstone of your exams.
Because this one chapter makes up a full 10% of your competitive physics exam. 10%. That is huge. But don't you worry, we're not just going to grind through it the hard way. We're going to reveal a secret weapon, a brilliant shortcut that makes this whole thing, well, surprisingly simple.
So here's our game plan for turning that confusion into confidence. First, we'll dig into why this chapter feels so tough. Then we'll get the basic language down before we unleash an elegant solution called Gauss's law. And finally, we'll put it all to work, all the way from forces to dipoles.
So, really, why all the hate? Well, the main reason this topic feels so difficult is that textbooks often teach it like a repetitive maze. They make you do the same complex calculations over and over and over again for different shapes, and it just makes it almost impossible to see the simple, kind of beautiful principles hiding underneath it all.
Okay, let's dive right in. Before we can find that amazing shortcut, we all need to be speaking the same language. And that means getting a really solid grip on two key ideas: the electric field and something called electric flux.
All right, imagine this. You go out and buy a really expensive, powerful source charge. It creates this invisible zone of influence all around it. That's the electric field. But how do you see it? Well, you use a cheap disposable test charge. Think of it like a piece of chewing gum. You just toss it in there and see which way it gets pushed or pulled. That tells you exactly what the field is doing right at that spot. Now, let's talk about flux. You've got those electric field lines streaming out from a charge, right? Well, flux isn't just about counting how many of those lines go through a surface. It's way more specific. We are only interested in the lines that pass through perfectly straight on, hitting the surface at a clean 90-degree angle. And to really see why students hate this chapter, let's try calculating the total flux through a simple cylinder, the old-fashioned way. It's a pain. You have to break the cylinder into 3 different parts, analyze all the angles for each part, calculate the flux for each, and then finally add it all up.
And after all of that tedious work, what do you get? 0. This right here, this is the pain point. All that geometry and vector math just to land on a big fat 0. You can totally see why students get so frustrated. There just has to be a better way. And thankfully, there is. A brilliant physicist named Gauss, supposedly in the final moments of his life, gave us a law that just cuts right through all this complexity like a hot knife through butter.
Now, here's a really cool bit of history. There's no fancy mathematical proof for Gauss's law. It's a law that was born from just pure observation and intuition. The story goes that he shared it near the end of his life, and, when someone speaks in their final moments, you kind of listen. We use it for one very simple reason. It works. It gets you the right answer incredibly fast.
So here it is, the crucial point. Gauss's law says the total flux coming out of any closed shape doesn't depend on the shape's size or its area or any of those complicated angles. Nope, it depends on only one thing: how much electric charge is trapped inside that closed shape. That's it.
So let's go back to our cylinder problem, but this time let's use our new secret weapon. Gauss's law takes that complicated, multi-step calculation and turns it into one simple, direct question. And this just brilliantly shows the power of this law. Is there any charge inside the cylinder? No. So, according to Gauss, the total charge enclosed is 0, which means the total flux is 0. Done. What took 4 steps and a bunch of math before now takes about 2 seconds of pure logic. It is a total game changer. Okay, there is one small catch. Gauss's law is amazing, but it demands symmetry. So if a problem isn't naturally symmetrical, we just impose symmetry ourselves. We draw an imaginary, perfectly symmetrical shape around the charges, and we call this a Gaussian surface. It's the key that unlocks the shortcut, because by making it symmetrical, we guarantee the electric field is the same strength at every point on our imaginary surface, and all the hard math just melts away. All right, now that we have our secret weapon and we know how to use it, let's lay out a simple, repeatable method for solving pretty much any standard electrostatics problem you're ever going to see. The method is actually pretty elegant. All we do is create two different ways to describe flux, and then we set them equal to each other. On one side, we use the basic geometry definition, the old way, and on the other side, we use the powerful simplicity of Gauss's law. By making these two things equal, we can solve for the electric field, E, and it's surprisingly easy. And applying this two-step method gives us some incredibly important and kind of cool results. For a charged sphere, it turns out the electric field is 0 on the inside, but then it weakens as you move away from the outside. For a really long wire, it also weakens, but a bit more slowly. But for a flat sheet of charge, something amazing happens. The field is constant, everywhere. It doesn't matter how far away you are, it's the same. Wild, right? So, now that we've got a good handle on fields and forces, let's switch things up. Let's shift our perspective to energy. This is going to help us understand concepts like potential energy and electric potential. And we can do it just by telling a simple story about how you'd build a collection of charges from scratch. So, imagine you're building a system of charges. You grab the first one from infinitely far away and place it down. Space is empty, there's no resistance, so it takes 0 work. Easy. But now when you bring in the second charge, you have to push against the repulsion from that first one. That work you do, that effort, it doesn't just disappear. It gets stored in the system as potential energy. And that simple story makes the whole concept feel way more intuitive. Okay, finally, let's tackle the last big puzzle of electrostatics, the electric dipole. That's just a fancy name for a pair of equal and opposite charges that are stuck near each other. Calculating stuff around a dipole seems really complicated, but you guessed it, there's another elegant shortcut hidden inside a new perspective. So the strength and direction of a dipole are all wrapped up in this one thing called the dipole moment vector. But here's the tricky part. It has a direction, and it is completely counterintuitive. You'd think it would point from the positive charge to the negative one, like an electric field line. But no. The convention, for historical reasons, is that the dipole moment vector points from the negative charge to the positive charge. Now, for a really slick trick, finding the potential at some random point near a dipole can be a mathematical mess. But instead of all that complex geometry, we can just use vector resolution. Just imagine splitting the main dipole vector into two smaller perpendicular parts. This simplifies the whole problem instantly. Why? Because your point is now on the axis of one of those parts and on the perpendicular bisector of the other. And the magic is, the potential along the perpendicular bisector of any dipole is always 0, which means we can just completely ignore one of the parts, leaving us with a much, much simpler calculation. From a boring 4-step calculation that just ends up being 0 to a simple law that solves the same problem in seconds, the story of electrostatics is this powerful reminder that sometimes the right perspective is the most powerful tool we have in physics. It really makes you wonder, right? What other complex problems, maybe in science or even just in life, could be made simple just by looking at them a little differently?